of superconducting qubits, pretty much any qubit platform of interest also has interesting transition frequencies in the microwave domain. So these devices are more useful generally. Now, I've been thinking about these problems for many years, but now these have become sort of a very hot area of research. So if you look at IBM's recent roadmap for quantum computing, interconnects form a big part of that. And if you look at Google's recent call for proposals for academic research, it's all about sort of microwave to optical transducers. So before I go into the details, I want to tell you why this problem is interesting, why this is hard, and what some new ideas are needed to sort of push this. So one nice way to think about these frequency transducers is to think of them as like sort of essentially quantum frequency conversion. So you have a photon at one frequency, you're converting it to another frequency. And if you think about it, RF modulators do that all the time. So one way to think about these devices is that you're trying to build a resonant modulator, but in some sense, the most efficient modulator that one can eventually imagine. So if you look at it in this picture, it becomes clear why this is a hard and interestingly hard problem. So any modulator in general you can describe the interaction by some overlap integral between the fields with which you're trying to engineer the interaction. So you have your pump field and you have the sort of sideband photons. And you immediately see what the problem is, that since if you want to go between the microwave domain to the optical domain, you have to somehow overcome this wavelength mismatch problem. So in the microwave domain, the fields have wavelengths on the order of tens of centimeters. On the optical side, you have fields on the order of microns. So if you want to engineer strong interactions between photons, then effectively you can't confine them to the same wavelength scale cavities because the wavelengths are very different. And this is the problem that acoustics solves for us here, is that if you now, instead of engineering a direct interaction between the microwave and the optical photon, if you convert the microwave photon into an acoustic field, then because the speed of sound is so much slower than the speed of light, you basically get access to microwave frequencies at sort of micrometer scale wavelengths. So now once you have micrometer scale wavelengths, then you can engineer very strong interactions with your sort of optical fields. This is the sort of bread and butter of what we do. There are other interesting advantages of pursuing acoustics, is that you also get very low dissipation inside these systems, and I'll come back to that later. Now, before I go on, I want to tell you that this is not the only way to build transducers. There are other approaches to building transducers, but I'll focus only on this because this is, I think, the one that has the most general applications outside of transduction. So in the second half of the talk, I'll tell you about some more near-term applications for these ideas. So this is the architecture for any of these piezoelectric microwave to optical transducers. If you're interested in this area, we wrote a review paper 2 years ago that goes into this area in much more detail. So I'd recommend that. But just in general, what any of these devices require is that you start with your signal from your superconducting qubit, or at least in these current experiments, just a weak classical signal. You convert it into an acoustic field. This acoustic field is injected into an optomechanical cavity, and describe that. And this is where the interaction is engineered. So like any nonlinear interaction, you have a strong optical pump field. And what you're interested in is this optical sideband that's scattered. And the key here is that you want to go through this whole loop. And if you do this properly, this optical sideband photon basically has all the quantum information that you started out with in the microwave photon. And that's the transduction problem. And why is this a hard problem? Is that you see that this is a multi-step process. Each step is being governed by some material or device parameters. And you essentially need to go through this whole loop with near unity efficiency. And in this talk, I'll focus only on one part, which is that once you get this sound generated, how do you inject it into these cavities with high efficiency? This is a big problem. Now, most of the current focus of this whole area of research is on pushing this transduction efficiency. So as I said, you want to link superconducting qubits together. You want the transduction efficiency to be near unity, but that's not the only requirement. What you want to do is to make sure that you can get high transduction efficiency with low added noise, and to do this both simultaneously. That's an even harder problem, so I'll just focus on the first part. So just some background on cavity optomechanics for those who haven't seen this. So very simply, what you're interested in is, as I said, one of the key requirements that you want to do is to design cavity structures in which you can get these very strong acousto-optic interactions. So one way to think about cavity optomechanics is sort of, it's the modern sort of integrated version of like traditional acousto-optics, except it has some new features into it. So one way to the characteristic device that you're interested in is a standard Fabry-Barot cavity with one of the mirrors that's mounted on a spring. And so now if you think about this, as this mirror moves back and forth, it changes the cavity resonance frequency. But what's important to point out is that there are two distinct effects that happen. So one is that the cavity frequency changes because the physical length of the cavity changes. That's sort of trivial to see. But if this medium was a solid medium and not vacuum, then as this cavity stretches back and forth, you develop periodic tension and compression in the cavity, and you get the stress-induced optical change in refractive index. So this is called the photoelastic or the electrostatic effect. And so you also get a second term that dominates. And what's important is that in the nanoscale devices, it's the second term, the stress-induced optical change, that's much larger than any sort of moving boundary effects that happen. And here are some horrendous expressions, but all I'm trying to is that this is a very simplified picture, but there are ways to calculate the effects of these acousto-optic interactions, even for the most complicated cavity geometries that one can imagine. So most of these interactions are engineered in these like so-called 1D optomechanical crystals. So this is basically a 1D photonic crystal, except that this photonic crystal, as I said, because the wavelength of light and sound inside the structure is identical, you can trap modes of light and modes of sound inside the same cavity. And so the acousto-optic interaction in these structures is very, very large. And just to give you some perspective, if you think of traditional acousto-optic devices and sort of bulk plane wave interactions, the acousto-optic interaction in these sort of nanoscale structures is orders of magnitude larger. And that mostly comes from the fact that you're confining both light and sound down to the wavelength scale. And this is now the sort of architecture around which you want to build this transducer. So what's the problem? The problem is, yes, you have very good acousto-optic interactions, but as I said, the quantum state starts off as a microwave signal. So you have to somehow be able to inject this microwave signal into this very small confined mode. So in some sense, the mode is very strongly confined. That's great. But because it's so strongly confined, you really have to be able to inject sound into these cavities from the outside. And that turns out to be a very hard problem. And I just want to go over some detail why this is challenging and why it's not trivial. So because especially if you come from an integrated photonics background, you might think this is an easy problem, because with photonics, it's trivial to couple to these 1D photonic crystal cavities, but acoustics is much, much harder. And one way to ask is, okay, why is this hard? Is if you ask what is the traditional way in which one can sort of couple sound into these geometries, is you can imagine that, okay, I take some shape transducer and I focus the sound down into the structure. But it turns out there's a massive mode mismatch. So if you look at the mode that you're interested in, the modes that work basically have, if you on some coordinate axis, have their predominant displacement along the y-axis. So that's the displacement you want to excite. But traditional focusing, so-called IDTs or transducers, launch most of their acoustic energy along the XZ plane. So most of the energy is focused along the XZ direction. So you need to design something that converts this mode into this mode. That's a very hard problem, and it's not generally known how to solve these kinds of acoustics problems. And I'm happy to answer questions about why this is much harder than the optical. So while this problem is trivial in the optical domain, it's almost impossible to design these structures in the acoustic domain. So that's what makes this very hard. And that's what makes these structures, the efficiency very weak, is that even though you can once you can get the sound inside this cavity, you can engineer very strong interactions. Getting the sound into these cavities in the first place is the real bottleneck. And this is the recurring theme throughout this talk, that we know how to make very small cavities very efficiently, but getting things into and out of them is a major problem.
Is it because of the acoustic velocity research, or what's the?
Maybe I'll just answer. Yeah, so there are few differences between the optical and the acoustic case. One is that with the optics, you can couple from the side through vacuum. With the acoustics, you can't, because you need a solid medium. So that's one major limitation. The other actually bigger problem is that with light, you can just sort of funnel the light in and it'll always stay in the center. But with sound, the sound starts hugging the edges, because the slow modes of sound are all on the edge. And so essentially you get mode conversion. That's the second problem. The third is that with optics, it's trivial to design a single mode waveguide geometry. This acoustics, it's intrinsically multimodal. So the whole mode transformation arguments, it's like doing mode transformation in a multimode fiber. So the combination of those effects makes this. Any other questions? Okay. So how do you get around this problem? So a few years ago, we proposed a solution to this problem, which is that in some sense, if you ask why this is a hard problem, you're asking the transducer to do two things at once. So there are two competing challenges that this transducer needs to address. One is that it needs to be well impedance matched to the superconducting qubit, so that you don't get microwave reflection. So that places a certain constraint on the size of the transducer. So to put in perspective, let's say that you want to design this transducer to be 50 ohms in the first place. But the same transducer also needs to take this acoustic mode and also funnel it down to this nanoscale dimension. So you also, so in some sense, you're asking one transducer to do both impedance matching and mode matching at the same time. And for the reasons I outlined just now, that turns out to be a very hard problem. So both impedance matching and mode matching become very, very challenging. And so the obvious solution is to break the problem up. And I want to design two transducers, two resonators that serve very different functionalities. Right. So this is what we propose. Instead of designing one resonator, you design your traditional optomechanical crystal that does the acousto-optic interaction. But on the other end, you sort of couple on the front end, you couple a piezoelectric resonator, something like a lamp-wave resonator, something that all RF engineers know how to design. And the trick here is that these two resonators, which have very different shapes and sort of even materials possibly, operate at the same frequency. And so then this becomes a coupled pendulum problem, and you can transfer energy. And if you work through the details, at least in theory, now you can do this more. Essentially, you got it around this photon injection problem. And especially in gallium arsenide, which is a weak piezoelectric system, you can show that with sort of suitable impedance matching, you can get like orders of magnitude improvement in transduction efficiency. The details are in this paper, but again, this is in theory now. I'll tell you why this is hard in practice. Now, one interesting side note is that when I first proposed this, I thought this was a completely new take on the problem, but like with most things, there are no new ideas truly. So this is actually, for those who are interested in this is actually the inverse of the process in which resonant gravitational wave detectors are read out. So there you have the opposite problem in that you have a very large mass, low vibration amplitude signal that you want to read out. And the way you do that is that you couple it to a small mass, large amplitude detector. So in some sense, this device is the opposite of so they are in some sense the same. But the key here is that by playing this kind of trick, you can get enormous improvement in overall transduction efficiency across a wide range of material platforms. And one other point I want to make is that if you stick to one single material to build these kinds of transducers, there's almost seems like there's an upper bound in efficiency. But the way to sort of address that is to go to hybrid material platforms where you use one strong piezoelectric for doing the microwave to acoustic conversion, and then you do the acousto-optic interaction in another material. And I'll point to that later. Any questions? Okay, so how do you go about building these? So the first thing is you need a photonics platform that can sustain this kind of like these devices are not trivial to sort of build. So you want to build, you have a platform that's capable to support high quality photonics, high quality mechanics, and good microwave so that you can get all these things together. So one of the first things I did at Bristol was to actually develop a big platform in gallium arsenide, which was inspired mostly by silicon photonics. So basically, you can take the standard silicon foundry platform and then sort of replicate it in gallium arsenide. And you can do that because at telecom wavelengths, the refractive indices of gallium arsenide and silicon are almost identical. You can just copy the recipes and design rules and everything. But gallium arsenide just happens to be a much more interesting material because it's piezoelectric. The only issue for many years with gallium arsenide was that people thought that the loss could never approach silicon, so because of the surface issues. But the transistor people have sort of figured out many of these problems ages ago, so you can borrow that as well. So if you do surface passivation properly, you can get losses comparable to sort of standard silicon foundry, not the best silicon foundry, but sort of can get comparable loss numbers. And here's a reference for it. So how do you go about proving these supermodes? As I said, really, if you want to do microwave to optical transduction, you really want to build supermodes around these 1D nanometer cavities. But that's a very hard problem for reasons that I'll go into. You want to pick a simple problem to just prove the idea first. And so that's what we set out to do. Is that instead of taking the modes of a nanobeam resonator, we instead try to hybridize the modes of a contour mode resonator or a lamp wave resonator with that of a simple waveguide. So this one way to think about this is that this nanobeam breathing mode that I've been discussing can be thought of as basically the breathing mode of just a standard waveguide, except that these holes keep this mode only confined to the center. So that's So even a structure like this basically has. And so that's the structure we did. So we basically built a device that looks like this. So you have grating couplers to get light in and out. You have a micro-ring resonator, and on one arm of the micro-ring resonator, you have this lab wave resonator that's built in. So then you get a mode hybridization, ideally between this structure and this. So what's the issue? Why is this a challenging thing? Is that in this experiment there are no tuning knobs. So we are actually looking on an accidental degeneracy. So as I said, these two resonators need to have roughly the same frequency, but if you have fabrication variation, then there's no guarantee that you can get these two resonators to cross. And that's why it's very hard to do that with nanobeam crystals, because there you have so many holes and so many dimensions that there is no chance of getting like this accidental overlap. On the other hand, with waveguides, you have much better control over lithography. There are much fewer dimensional parameters. So if you do a parameter sweep, you can always find a set of devices where these two frequencies end up sort of coming within one line bit, so you get a crossing between them. And so that's what you do. So search among devices. And what you see is that once you get this mode hybridization, you get this characteristic splitting of the resonance frequency, you get this doublet. And at the right super mode, you basically get this massive improvement in transduction efficiency. So that works. And when you don't get this hybridization, even though you basically the transduction is much, much weaker. So the idea works in principle, but as I said, I wasn't very happy with the experiment because one of the issues here is that we had to rely on making a bunch of devices, tuning parameters slightly and finding ones that gave you this sort of accidental crossing. What you ideally need to do is to have some direct way of measuring this, that this mode hybridization has occurred. And so that there are three ways of doing this, all of which we're trying right now. One is that you can actually look for the thermal noise spectrum. You can look for see if the mode shows up in the noise spectrum. For reasons, this is very hard. But the other two things, and these are generally useful outside of this area, is developing good acoustic imaging techniques. So right now, unlike with light, where we have very good ways to visualize light flowing in circuits, we currently don't have good ways of seeing how sound flows in these sort of nanoscale devices. We don't have any way of figuring out. So we only have like these microwave endpoint measurements where we launch some sound, we detect some sound. And we really don't have any good ideas about what happens to the sound as it hits all of these interfaces. So new microscopy methods are essential. I can tell you something about that. But the other key metric is that ideally what you want is to be able to tune one mode across another. And this is very hard because what you want to do is to tune two mechanical resonances without touching the optical resonance. So that makes it. We're working towards all of that. So where are we with these first experiments? So in the first experiments with this supermode structure, we showed that you can get a 10 to the 5 improvement over state of the art. That works. And this works mainly because now you can get sound very efficiently into these structures. But in the first generation devices, the device performance was purely limited by the bare cavity parameters. And optical loss is easy to fix, but the mechanical loss is the bigger problem. You can see that the sound as it vibrates back and forth, there are all these tethers that were holding the structure in place, and you can get a lot of leakage out of this. So these are problems that are in principle easy to fix, but sort of hard in practice. So our current generation devices are a couple of orders of magnitude better, but even with sort of state-of-the-art improvements in all of these parameters, there's a limit to how well you can push with a single material, because as I said, gallium arsenide has a weak piezoelectric coefficient. So you need a large number of periods here to get the sound, to get the microwave efficiently coupled to the acoustics. And that ultimately poses a limitation.
So what's the trade-off? So you're getting a large gain.
Yeah, the trade-off here is that the coupling strength goes down. So now if you imagine the mechanical mode is no longer only inside the waveguide, a part of it is spilt into this region. The optical field doesn't see this. So the interaction strength goes down. So you basically the per photon interaction strength is down, but the phonon injection efficiency is higher. But because it's a rate equation, you can always balance it out. So subject to the fact that if you have high enough quality factors, even if your per pass interaction is weak, you can trade off against having more passes to the same interaction. That makes sense.
So this too slows down it.
The bandwidth goes down. There's
10 to 5 times.
no. When you get a mode splitting, then the bandwidth is the splitting between the modes, not the individual. So you still the bandwidth goes down, but not as much as. So, I mean, one question is basically what sort of bandwidths you need to transmit qubit states, and the numbers we were told by the qubit people is like 1 megahertz is a good.
Well, I mean, it's going to be now, in the future.
No, but the superconducting qubit people cannot do fast gates because they're worried about sort of higher order states, so the pulses that the pulse shaping places a limitation. So I don't know. I'm not an expert on that. But as far as I understand, but 1 megahertz is still out of reach of current experiments. Yeah. Any other? So I said like so where is this is where we are, but I want to tell you also where the field is. So as I said, there's a limitation to how high you can push this efficiency if you just get one material.
Quick question.
Yeah.
Measurement of this is done at low temperature?
No, room temperature. Yeah. Low temperature. Yeah, I'll come to that. Yeah, the second half is where. Yeah. So I said the temperature is interesting, but it won't change things here because we are so limited by clamping laws that cooling down doesn't help us. The second part, it will make a difference. Yeah, so where is the field? As I said, the one way to really push this efficiency, as I said, is if you separate the problem completely, where you say that, okay, I'll remove this constraint of sticking only to one material, I'll increase my complexity of fabrication considerably, but now if I can build structures like this, where now you have the same 1D photonic crystal, but now on the end of it, I'm able to put down a small slab of lithium niobate, then I removed all the trade-offs in the structure because now the mode hybridization happens between this small block of piezoelectric and the cavity. So the reduction in the coupling strength is finite, but it's very, very small. And with these structures, the state-of-the-art devices are at like 5%. So per photon construction efficiency is 5%. I mean, I think this is a marvel of fabrication. Like getting this block one is not trivial at all. I always thought that this was people have been able to. Yeah, because now with lithium niobate, you can get K effective squares of on the order of 25 to 30%. So that means that with 3 electrodes, you can get impedance matching to 50 ohms. That's the trick. Where are we going? So, I mean, because of these problems, personally, I've been trying to sort of move away from these optomechanical crystals and move instead towards sort of traveling wave phonon geometries. There are a couple of reasons for doing that. One is that with these nanobeam optomechanical crystals, at low temperature, you get all sorts of parasitic heating effects because the heat of the surface to volume ratio in these devices. And the other issue is that there's a maximum frequency that you can reach simply because of the fact that you have to make these very, very small holes. And so one way to avoid this problem is to move towards traveling wave geometries where you work with these essentially bulk phonons inside the structure, but bulk phonons that are confined in some interesting fashion. And with these geometries, you can hear the acoustics is very, very good because the phonon injection efficiency is near unity. So if all the phonons get launched into the right mode, they go into the right place. Everything. The hard part is the optics because now you want to build high Q optical cavities with fibers aligned around the system. So we can get the acoustics working. We're still working on getting the optics aligned because doing this inside a cryostat is very, very hard. Something that so we have a collaboration with people who know how to do this better than us. So, any questions?
Yeah.
Yeah.
You have to be coplanar with your acoustic and optical, or it can be orthogonal. Okay.
No, so to get the depends. So if you want to do Brillouin scattering, then the highest gain comes for the coplanar geometry. You can do the sort of contracoupled structures, but there the issue is that then so if you're coplanar
cases, the previous cases, all the nanobeams here.
they're orthogonal, yeah.
So the one that you showed on the link, that's orthogonal.
They're all orthogonal.
And then on the deep front, I have not seen that paper at lithium niobate. So
yeah, so they're all orthogonal. They're all the same idea. They're all orthogonal because that's how you can get this efficiency to work.
Right.
But here it is not orthogonal for exactly that reason. Is that if you want to build an optical cavity, you want to get maximum interaction between the two fields. With these bulk geometries, the only way you can do that is, otherwise the problem is that if you do 90 degrees, then a lot of the field will be outside the interaction region. So then your restrictions on optical Q become prohibitive.
Like, what about just making a in-plane optical cavity and your acoustic cavity is
Well, then you don't get phase matching with that. So with Brillouin, if you want to use Brillouin scattering with traveling wave phonons, then phase matching becomes. So you really need to be phase matched. If I'm understanding your question correctly.
No, we'll talk.
Yeah, sure. So the only nice thing that in this design that we do is that you might have heard of traditional bulk acoustic wave resonators. Those don't work because the field is confined under metals, which kill your acoustic Q and your optical Q. So we work with these other modes, which are called X bars, which are shear horizontal modes. So you basically, the field is now confined in between the electrodes, and we can shape it further by building these like lenses on top that sort of further shape the field. So you can get very nice acoustics. The hard part is getting the optics to work as well. That's work underway. And then what else can we do? Well, we have this nice gallium arsenide platform. We can really push the modulator side of it. So try to build really good active devices. So why gallium arsenide when all this thing about lithium niobate? Well, it turns out gallium arsenide has two advantages. One is that it's remarkably a space qualified material, so it's radiation hard. So turns out that putting materials in space is very hard. People want to work with existing materials that they know work well, and gallium arsenide has no bias drift. So turns out that there are companies that specialize in these. But what's unique about our modulators is that we use this very nice trick that because you use the R14 coefficient, then you can play this nice trick that if you have a field that's going vertically through the device, then light that goes horizontally, say along the x-axis, and light that goes along y-axis, will see opposite phase shifts. So you can build push-pull modulators with. So these are the first push-pull modulators that get developed. So we can see this effect, but the fabrication is insanely complicated, as you can imagine. Happy to chat more about this. Okay, so with that, that's the first part of the talk. I talked mostly about bringing ideas from sort of RF MEMS and acoustic wave devices onto integrated photonics. But in working with all these sort of quantum transducers and working with sort of waves in confined systems, I got very interested in sort of acoustic devices in general and sort of bringing ideas from silicon photonics to acoustics. And so that I'll tell you briefly. So this basically began with a very simple observation as I was looking into transducers. So most of you should know that basically all the filtering in modern smartphones happens using acoustic wave devices. So each modern smartphone has on the order of 50 RF filters, which are all acoustics based. And so there are billions of acoustic devices floating around every single. But no matter what acoustic device what material, what device geometry, what sort of frequency, all acoustic devices work essentially as quasi-plane waves. So there is no strong confinement of sound in any commercial acoustic system as far as I know. And this is very surprising if you come from integrated photonics, because I mean, I'm not that old, but I've lived through the revolution where if you go from optical fibers to silicon photonics, the scale and complexity of things that you can do are just orders of magnitude more interesting. And so the natural question becomes like, what can we do with acoustics? So if you can now funnel sound waves through these systems, can you do more than just replicating these things? Can you do something on the order of this kind of complexity? So can you do active devices? That's what I want to show you. So you need to pick a platform. So there are, in principle, any waveguiding platform works for sound. So we choose gallium nitride on silicon carbide for a few reasons. One is that gallium nitride is a semiconductor, so I'm mostly interested in engineering acousto-electric interactions in these waveguide geometries. I'll come to that. But one of the nice things with GaN is that the material has been optimized so much from sort of other directions. So basically, because of high power RF and power semiconductors, people have figured out how to grow gallium nitride on silicon carbide with sort of very little lattice defects. And even at IISc, there's some very amazing work on this. So we just take those substrates, and the acoustics in these devices is amazing. But mostly there's a very mature foundry architecture. So once you can make these devices, you can sort of get them printed in a foundry, even though we are not at that stage. But the ultimate goal is basically that in principle, this is the only platform that gives you the ability to not just put passive devices, but do this active-passive interface, which is what we want to do. So what can you do that you can't do otherwise? Well, I want to show you just two results from where we are. One is that you can start building photonic acoustic analogs of photonic devices, and you can build these acoustic microring resonators. So the question is, why would you want to do that? Well, in some sense, this device has no clamping loss. So the Q factors that you can get. So the sound is sort of launched here, it couples in, and it sort of rings here. There is almost no excess dissipation inside this structure. And we were stunned by the Q factors that we can get even in like devices fabricated in academic clean rooms. So the FQ products are gigantic. They start exceeding sort of material limits. So one way to think of that is that you can ask what is the Akiza damping limit. This is a very simple, it's an approximate limit, but it's a good sort of rule of thumb to estimate where things are. And you can see that even in our academic devices, there are many devices that we can easily exceed this. That's because there is no, in traditional devices, you're always reflecting the sound from metals, either from in F bars or in source. And you always get some excess dissipation, scattering loss. There is none inside these devices. That's one thing. The Q is very high at room temperature. We're just starting to do, but it's much more interesting to do the Q factor measurements at low temperature, but I'll pause on that for now. But what's the other thing that you can do? Once you can get sound into a waveguide, you can sort of just take the waveguide and spiral it into a sort of long spiral microring resonator. Sorry, a long spiral waveguide. And then you can do stuff that basically has no classical analog in devices. Since that now you can get delays on chip that are like microseconds and sort of we push this up to like 4 microseconds now. And just to give you some analog of so this, the equivalent cable delay is like 750 meters of cable. So now you've taken 750 meters of cable, and now this is in an area that's less than 0.25 millimeters squared. All that's good. What's the issue? It's the insertion loss. As I said, we can get very large delays, but not much of the signal makes it to the other side. And to be honest, the loss, so once the signal gets into the waveguide, it's very good. As I said, from the rings itself, most of the loss happens at these two interfaces. We are not able to funnel sound into these waveguide geometries with high efficiency. If we can solve that problem, then basically this opens up any number of, and it's, as I said, this is the same problem that came in the first one. Like figuring out how to get sound into small cavities is hard. Okay. I have 10 minutes. So with that, I'll go to the final part, which is one of the more interesting parts of this, is what can you do sort of pushing acoustics beyond sort of its traditional operating regimes. And so this comes about because so I have a long interest in sort of spin interfaces and detecting spin systems. But if you look at traditional electron spin resonance systems, if you look at a traditional ESR spectrometer that you can get from Bruker, and you ask what is the minimum number of spins you need to get a signal out of this system, that number is 10 to the 12 spins at room temperature. And if you now compare that with any sort of fundamental noise limits like thermal noise, it's like 7 to 8 orders of magnitude above or any of the noise limits. And that's very surprising because very few modern devices are that far away from sort of fundamental limits. So you might want to ask, okay, why is this that we are so poor at that? And if you think about this, is exactly the same problem, is that effectively the cavity that is used to interface with these spin systems is a sort of a traditional microwave cavity. So you're trying to put centimeters scale fields and trying to interface with sort of small volume samples. So that there's this huge size mismatch. And so the natural question becomes, can you use sound in some ways to do this interface? And the whole argument here is that if you can, then there's this very nice symmetry in the Hamiltonians for electric and magnetic dipoles. The energy terms are almost identical. And so we know how to manipulate electric dipoles in cavity QED for almost 50 years, but not much has been done in terms of magnetic dipoles. And this is what we want to do here. And so the goal here is to try to figure out other sort of geometries in which you can do single spin readout. So basically a single spin inside a cavity, can you tell if the spin is up or down? And like with traditional cavity QED, what you need is a sort of small mode volume IQ cavity, RF cavity. Why is this interesting? So I want to take some time and sort of over this. And so this is not the, so mechanical systems have been used to detect single spins in the past. And if there's this very famous paper from Dan Ruger at IBM that some of you may have seen, where they used an AFM cantilever to this magnetic resonance force microscopy. And they showed that basically single spin detection sensitivity was feasible, except that this is a very complicated system and it's not applicable to general ESR. But as a side, they wrote another paper where they actually compared the signal detection sensitivity of mechanical and inductive or electromagnetic resonance. And they basically came to the conclusion that in principle, mechanics can give you an advantage if you can build small mode volume high Q cavities. Not a sort of topic, but it's good to see that this was realized many years ago, except that they didn't sort of make the connection to acoustics that we'll do. One way to think about this is that recently superconducting cavities have been used to detect single spins. So again, you can use a very high Q small mode volume cavity, and you can, so there's no restriction. So basically, anytime you get access to a very high quality factor small mode volume cavity, you can effectively do cavity QAT with it. The issue with superconducting cavities is that there you have very high quality factors, but the mode volumes are I mean, still an electromagnetic cavity, so the mode volumes are moderate. But the main issue is that it's restricted to millikelvin temperatures, so you can't really do anything with that. Sort of, if you want to do any biology, for instance, or chemistry, this doesn't really work.
So, I mean, you really have a lot of mode volume to play with, because at the end of the day, your mode volume is determined by the frequency. So what will be your
Sorry, the mode volume of which?
the mode volume?
Yes, the mode volume. Sorry, so this is relative to the electromagnetic mode volume, right? So so if you now take an acoustic, as I showed, if you take an acoustic cavity and you generate an electromagnetic field through the acoustic field, then the effective mode volume is 10 to the 15 times smaller because the wavelength shrinks by 10 to the 5. So then the spin detection sensitivity goes up by 10 to the 8. That's the trick.
So from electromagnetic wave, they're coming to the.
It's the same. It's the same reason your cell phones can work, right? So one way to think is, why does this? How is a cell phone even possible if you're detecting signals at 3 gigahertz? That's 10 centimeters in size, right? So how are you able to pick up 50 signals? And it's because you're shrinking that the antenna shrinks it down.
But the omega naught remains the same.
The omega naught, yeah, will remain the same. Yes, the omega naught stays the same, but the lambda shrinks. And so but because it goes as lambda cube, so if the lambda shrinks by 10 to the 5, the lambda cube shrinks by 10 to the 15. So you get orders of magnitude. In theory, I'll show you where we are experimentally, but the ideas hopefully should work. Yeah, so this, so this, what is this? Sorry, it should be to the 4th. There's a typo here, but yeah, so one issue with piezoelectric devices is that traditionally you don't think of piezoelectric devices and magnetic fields. You always think of piezoelectric devices as generating electric fields, but this is an approximation. So that's usually called the quasi-static approximation. And all approximations break down at some point. The question is, what limit do you take it? So one way to see this analogy is that surface acoustic waves and surface plasmons are in some sense identical. So they are single interface waves. And if you take a surface plasmon, you can see this just by analogy, that in a surface plasmon, when you solve the dispersion relation, you start with the magnetic field, and you sort of solve the whole thing. So this is exactly an identical scenario where instead of the fields terminating on mobile charge carriers, here it's the surface polarization that terminates the fields. So there is an evanescent electric field that curls due to this phenomenon called spin momentum locking. And so there is a magnetic field that has to exist. It's usually very, very weak, but the question is, how weak is it? And more importantly, how does it scale with frequency? And as I said, sorry, so it scales with the square of the frequency. That's the key result. And there's a paper that I'll point to. But this is a general result, no matter what field is it. And this is true of all evanescent waves on a surface. This phenomenon called spin momentum locking. So when you have an evanescent field on a surface, the electric field has to curl in a certain orientation depending on the direction of wave propagation, which means that now if you apply Maxwell's equations, the magnetic field has to exist. And yeah, so one way to see that is that so now again so you're taking a field and you're confining it to lambda cube. And then you also, so that gives you a 1 over frequency cube. And then you also get because the frequency scales, so you get 1 over omega to the 4th power. And that is how the energy density scales. Because the energy density scales with the 4th power of frequency, the field scales with the square. That's a hand waving approximation. The easier way to see this is with this. Is that clear to everyone? So you're taking the same field, you're confining it to a mode volume that scales with lambda cube. And so since it's lambda cube, it's 1 over frequency cube. But also if the field is oscillating at a higher frequency, so then it scales as the square. Yeah, so one point I want to make is that this is different from any previous. If you look at acoustic fields and spin systems, there's been a lot of work, but this is different in the sense that we are using the piezoelectric materials purely as field generators. So we're trying to synthesize fields here. We're not interested in sort of magnetoelastic effects or anything like that. We want to be able to use these cavities to do any electron spin resonance experiment that people have traditionally done. So there is no magnetic coefficients that should exist inside this. So how do you prove this effect? The first thing we thought was, okay, we can just try and detect single nanoparticles inside confocal acoustic resonators. This turned out to be very, very hard for reasons I'm happy to go into later. So what we needed was a very high Q magnetic mode that we could sort of probe with the system. And so for that, we use these polished gig spheres. These have very high Q ferromagnetic resonance. And the idea is that as the ferromagnetic resonance is easily tunable by applying a DC magnetic field. So as you cross the DC magnetic field across the acoustic resonance, you should see basically an excess absorption as this occurs. And you see that quite clearly. So when this Magnon mode crosses across the SAW resonance, you get this like complete extinction. That's a good result. And you can see the details in this paper. So you can see that the extinction is almost complete, and we were quite surprised when that happened. But again, this is a good result, but it's not what I ideally want, is because to really prove that this is what is happening, you want to confirm one of two things. You either want to confine that the frequency scaling goes as this x squared that I was talking about, or the fact that you can get this because it's a focused acoustic field, then you get strong absorption just at the focus, but not at the outsides. That turns out to be almost impossible with a sphere of this size. You can see that the problem is that it's very hard to know where the contact point is with our current imaging setup. So even though we can do raster scanning or anything else, it is very, very hard to know where. So to get these maps of frequency scaling becomes impossible. So this is, I'm hoping for ideas from the audience. If you have better ideas on how you can have nanoscale spin systems that have very high quality factors to verify one of these two effects. Yeah, so sorry, this is the right expression. It should scale as the square of the magnetic field should scale as the 4th power of the frequency.
So just a question.
Yeah. In this, yeah, so this is a very good, even the reviewers asked exact questions. So the mode volume should be the same as the mode volume of the electric field, which should be about 5 lambda cube. That's in theory. The more interesting question is how many spins are we probing? That's very hard to know because we are not even sure which Magnon mode. So I'm calling this the Magnon mode, but in a sphere of this size, there are multiple magnetostatic modes that actually occur inside the system. And it is not obvious to me, like without doing mode imaging of some more sophisticated kind, I can't really tell how the coupling is actually happening, because so some fraction of the spins are in the evanescent field, but the size of the sphere is much larger than the evanescent tail. So the wavelength is on the order of a micron. So after about 5 microns, there should be almost no magnetic field present, but we are still able to excite macroscopic mode of this. The number of spins. I need to think about that. Yeah, that's a good point. Yeah, I haven't thought about it.
Why does the evanescent field? How much does it do inside?
Yeah, so it drops off with the wavelength, with the acoustic wavelength of the electromagnetic. So about a micron and a half. Yeah, systems. Yeah, so we did the experiment, and then the referee asked us, why is this experiment working in there because if traditionally when people do EX spheres, they excite it with an electromagnetic field which is centimeters in size. So then you can see the magnetostatic modes of the system. The question is why. Essentially, we are doing the equivalent of point coupling to a sphere, and it's still working. So the argument that I wrote was that at least in optics whispering gallery modes, you can excite through point coupling with this. But I don't have I have some follow-up experiments in mind, but it's a good question. Okay, and then the last 2 minutes, I'll tell you the most exciting part of this, which is what are the prospects for actually detecting single spins or individual nanoparticles with this. And so the idea is that if this cavity mode volume is of the size that, so again, this is the magnetic fields mode volume. If this is the size that we think it is, now, so one nice development that's happened since we put this paper on the archive is that now, so as I said, because traditional piezoelectric devices impose this quasi-static approximation, even finite element solvers like COMSOLVE impose this. So when you solve for the modes of a system, you can't solve the magnetic field using COMSOLVE because it will force it to zero. On the other hand, there are people who have figured out ways around it. So now we can actually calculate the magnetic field using something called weak forms. And so now we have very good at least evidence that the mode volume should be this size. Have some better estimates. So now if you assume that the mode volume is size that this is, and then you just plug in some numbers, you can ask the question, what is the minimum spin detection sensitivity? So with a signal to noise ratio of 1, what can you detect? And the question is, what you do is that you just plug this number to 1 and ask when is single spin detection feasible. And it turns out it works if you have at a frequency of over 10 gigahertz, if you can get a Q factor of 10 to the 5 at low temperature, then this is within reach, which would be remarkable. So we're going to try that. We're not yet there. Sorry? It's the dephasing time constant. Yes, but not so large for like donor spins and silicon. So the platforms where it's all the quantum computing platforms, the qubits, they are much 50 milliseconds is okay. For like donor spins and silicon is the platform we're going to try. Not even that high. Yes, you're right that for general spin systems, but to root single spins, ideally we want to use it to do. So the reason to do all of this work is that right now, if you have spin qubits, for instance, there's no way that you can, in some sense, if you can read out electrically single spins, you can also address them without crosstalk. That's the main reason, is that you can now get very low crosstalk addressing. That's where they. Okay. I think I've already overrun. So I just want to tell you that, yeah, so I've spoken about 3 problems that look very different, but I hope that I've convinced you that it's a very exciting field. Okay, taking sound waves and sort of working with nanoscale cavities I mean, if you can get sound waves into and out of wavelength scale cavities with near unity efficiency, a variety of problems, not only on the quantum front, but sort of more aligned areas in the near term also open up, especially for sort of RF front ends. But one thing in working on this problem, I tried to write in my abstract, is that this is one instance of a much more general nanoscale wiring problem that these days with access to nanofabrication is sort of democratized in a way that almost anyone can build small structures. So, but the real challenge now is sort of getting information into and out of these small devices with near unity efficiency. So with that, I'd like to thank all the people who did the work and the funding agencies.
Can I ask for materials from the
Yeah, sure.
So I sort of did follow why GaN on silicon carbide and why not aluminum nitride.
Aluminum nitride on silicon carbide. Yeah, so you need a slow and fast. So to do any kind of waveguiding, you need a certain conditions on the. It's like with optics, the velocity of your field in the guiding layer should be lower than that on the substrate. Otherwise, you don't get total internal reflection. So there are very few natural platforms that give you that combination. So for example, silicon on insulator will guide light, but will not guide sound. So that's one reason to pick GaN on silicon carbide, because it's one of the few platforms that allows that. But our main interest is that it's because gallium nitride is a semiconductor. So we are interested. So one way to think about this is that why do you want to do this in the first place? I mean, you have very good filters in your smartphone. What you don't have is basically combinations of filters with amplifiers. So right now they're discrete blocks. And so if you want to, it's the interface that is hard. And that's, you need a semiconductor to that. That's the reason.
Second question is the last part. So is it, don't you get similar effects from using magnetoelastic or
Yes. Yeah, magnetoelastic, yeah, but those have been well studied. But what we want to do is to do electron spin resonance. So basically, in materials that have very small magnetoelastic coefficients, how do you detect few spins? The only way is to shrink the field so that the local field strength. So if you have some interesting biological samples that have, say, 10 spins, and you want to detect 2 ESR on that, right now there's no way you can do that. So actually, even if you have 1,000 spins, you can. That's where we are, and that's what we want to go to. Is if you have very small samples that are, like, for example, drugs is the obvious one where people, when they do drug development, it's like this massively parallelized thing where you generate like 1 million compounds with very small volumes, and you want to characterize them very fast. But ESR cannot be done on them because you just don't have the quantities to probe. I'm interested more in the fundamental, but I think those are the kinds of applications that. Yeah. No, that's the point. It's like a photonic structure. It's exactly the same. There is no that's what, because it's like when you have a photonic ring, there's no leakage into the substrate. Same thing. Sound is guided. That's the whole point. It's exactly the same thing. Gallium nitride is very, the silicon carbide has, I think, the second highest natural acoustic. So after diamond, it's the second highest. So it's a very good substrate for guiding. Like Saurabh wrote a paper where he also showed that the silicon carbide has best mechanical properties. So if you, this AKE limit, so one of the reasons that this AKE limit, this Akiza damping limit, is a material specific limit for different materials. So silicon carbide has, by that metric, it's the best mechanical material. And so if you put A on silicon carbide, you also get the advantages of silicon carbide. Does that make sense?
So the telecom wavelengths, which is a few droplets.
Yeah.
Highly nonlinear liquid medium. So you view on those as possible ways of this function.
Yes, there are many ways to do this, but the so I think that one is very exotic. I would say that's not. So ultimately, when you want to build these kinds of transducers, you're not interested only in like one transducer. You want like at least thousands per biostat. So it has to be some chip scale platform that works. So I'm sure that. But in terms of acoustics, why is acoustics interesting? Is that so quantum transduction is an important problem, but it's also a slightly niche problem in the sense that it presumes, on some sense, that superconducting qubits win out. But acoustics as a development, I think, has much more broader applications.
So why is it that it works in such a strong level on this sort of nonlinear fluidic droplets, even at a single level, as opposed to why is there a fundamental difficulty like solid platforms?
Yes, but he's just doing optomechanics of fluid droplets. He's not doing microwave to optical transduction, in the sense that he's using light to sort of, so basically these, whatever the bubbles of helium, basically, because in some sense, when you create a bubble in a fluid, there's a massive refractive index change that you get. So, but I don't think you can use that to transport a qubit state, because you need to somehow get the microwave to drive that bubble oscillation. Yeah, sure. Yeah. Maybe I'm misunderstanding the question. Yep.
Temperature, because you said you
Yeah.
say something about temperature.
Yes. Sorry. Yes.
So
Yeah. So I'll say that I realized I didn't have the view graph here. So why is it the temperature is important? Because one of the you're the expert in the audience, so I should sort of be careful of what I say. So one of the things that's not known, and so I've spent a lot of time working on dissipation in sort of photonic platforms, is most of the dissipation in these in guided wave systems comes from surface states. So but surface states in photonics, we have a good idea of how to passivate them. So you have this aluminum encapsulation in compound semiconductors and so on. But what's not known is how much any of these ideas can carry forward to the acoustic domain. So when you have these acoustic waveguides, can you passivate them with encapsulation? I don't think that's true, because we don't understand what two-level systems are. So the way to check that is to measure the Q of a very high Q system that has no excess loss. So it's very hard to find systems that have no excess loss to measure the low Q to find the intrinsic limit. Because one of the predictions that should hold true is that if all other sources of loss are removed, the acoustic dissipation should scale as 1 over T to the 4 or T to the 6. But no one has seen that because it clamps below 5 Kelvin. And no system except in these nanobeam optomechanical crystals at millikelvin temperatures where the Q just goes up. And that's what we're trying to do, is to figure out results are not there yet. But that's the temperature argument, is that I think the microrings are the only way that you can reach that regime where you can see this, or at least answer the question about what role does surface play in dissipation.
Yes, follow up on that gap.
Yeah, sure.
So I understand the issue is you put more sound into your link, right? So
Get any sound in. Yeah.
So if you break it up for me and
Yeah.
think of it as a materials problem, so what is it that, or think of it as any problem?
Yeah.
Yeah. How can you put more sound into it? So what is the solution to that?
Yeah. So can I sketch something? Can I draw something?
Yes.
Yeah. So as I said, the issue is that basically the sound comes from. Let's say you start with a microwave signal that comes from a transmission line. Say that's 50 ohms. So you want to design a transducer that converts this microwave signal into an acoustic wave, and you want to get all of this acoustic energy into this waveguide. This is the problem we want to solve, is that this not getting this part is solved. We know how to get all the microwave energy into sound. That's why your filters, smartphone works so well. All the problem comes in after taking this plane wave. Now this is like, say, 20 lambda size. This is 1 lambda. It's this focusing problem that we have. It isn't. Yeah, it's a
people solve it.
yeah. So it's true in every material. New ideas. We have some ideas. You can solve this in all of these problems. And I told you why this is a hard problem. Or the traditional photonic approaches don't. Because acoustics is fundamentally. So this is trivial in photonics. We know how to solve this very easily. So we do this routinely in memory. So with light, you can get light into and out of these cavities with near unity efficiency. So basically, this transfer, you want it to be unity. This is unity for light. This is on the order of like 10 to the minus 5.
Any other question? Not that time.
Thank you so much for coming.
Everybody, thank you.
Well, this is taking pictures for you.
Thank you.
Thank you. Thank you.
Krishna.
Yes.
So
Sorry. Yeah. So outside.